Welcome back, ladies and gentlemen, to another AP Chemistry video. Today, our focus is going to be on something fairly simple, yet, in all honesty, commonly missed on the AP exam, and that is the concept of photoelectron spectroscopy. That is essentially a graphical analysis, or graphical picture, if you will, of an electron configuration. The bigger picture of this really allows us to get a better fundamental understanding of how Coulomb's law actually plays a role in the attraction of both the core and valence electrons to the nucleus of an atom, and the strength of the ionization energy, how much energy is needed to remove those electrons. And there's just a lot of really useful information that we can get from a very good, accurate photoelectron spectroscopy diagram. So that's going to be our big focus for today, is ensuring that we can go through and analyze them. So what do we need to know from this information? Well, the energies of electrons in a given shell can be measured experimentally with photoelectron spectroscopy. The position of each peak in the graph is related to the energy required to remove an electron from the corresponding subshell, and the height of each peak is proportional to the number of electrons in that subshell. So as I mentioned before, what this means is that we are looking at essentially a visual representation of an electron configuration. And we can use this information to determine the types of atoms that are represented by that photoelectron spectroscopy. We can determine relative strength of attraction to the nucleus of those electrons and the relative amount of energy needed to remove them, and something called binding energy. So lots of information we can really get from this. So if I take a look at the graph on the right-hand side here, this is a photoelectron spectroscopy graph, and it is unique in that it shows the relative number of electrons that are found with each subshell. So if we take a look on the right-hand side here, you see that you have 3 peaks. And each peak on the graph represents a relative subshell that's related to an electron configuration. As we know, when we start off electron configurations, that is 1s2, 2s2, 2p6, the 1s sublevel is the one that is closest to the nucleus, then the 2s, then the 2p, etc. Things get a little bit dicier when we start getting into the d and f subshells, so we really don't focus on those in this particular course. However, because the 1s subshell is the one that is closest to the nucleus, it is the one that is going to be most attracted to the nucleus and has the highest binding energy. So if we go from left to right, we're essentially reading the electron configuration. So the first peak in the graph there is 1s, and you notice that it is 2 electrons high, representing 1s2. The second peak is 2s, and again, 2 electrons high. And then the third peak there is 2p, and it goes up by 4, 1, 2, 3, 4. So again, we know the element in question here if we know the element that ends in the electron configuration 2p4, in which case that would be oxygen. But we can also do some analysis and compare and contrast different photoelectron spectroscopy graphs and get an understanding of the attraction of those electrons to the nucleus when we compare them to other elements on the periodic table. So I want you to take a look at the 2 axes that are present here. The x-axis is normally labeled as binding energy, and that's how much energy is essentially needed to remove the electron. It really focuses in on how much it's attracted to the nucleus. But notice that it is a logarithmic scale. So you start off at 1,000, 110, 1, so it gets smaller quite quickly as we get away from the nucleus. And the y-axis is typically labeled with the relative number of electrons that are present. So again, very easy to analyze this graph and determine what element it is and what subshells we're looking at. So the graph reads from left to right as you're reading an electron configuration. As I mentioned before, the first peak there is the 1s sublevel, the second peak is the 2s sublevel, and the third peak is the 2p sublevel. And again, we can look at the relative number of electrons that are present in that sublevel. The 1s is 2 electrons high, the 2s is 2 electrons high, and the 2p is 4 electrons high. And so this is a neutral atom of oxygen. We can write the full electron configuration for this just like how we normally would. And again, it's a visual representation of an electron configuration. There isn't a whole lot to talk about with this, so I feel like I'm repeating myself over and over again, but that's the nature of this particular graph. So comparisons of peaks of different elements show us some key components of Coulomb's law. So for example, let's say we had an atom of fluorine, and we wanted to talk about the 1s peak. And we want to know whether it's going to be to the left or to the right. Well, if we look at the position of fluorine on the periodic table when compared to that of oxygen, fluorine is to the right of oxygen on the periodic table. That means that it's going to have an extra proton in its nucleus, so the 1s sublevel is going to be more attracted to the nucleus of fluorine than it would be of oxygen. So the peak is going to be to the left due to the increased nuclear charge that's present in fluorine. Fluorine would have 9 protons in its nucleus, while oxygen only has 8. And so the increased nuclear charge results in the 1s peak being closer to the nucleus than that of oxygen. So the peak would shift over to the left. If we looked at the 2p peak of fluorine when compared to that of oxygen, it would also be shifted to the left. However, Since the number of electrons increases in the peak, it gets higher by 1 electron. So the same rationale is here. Because we have an increased nuclear charge in the nucleus of fluorine when compared to that of oxygen, we're going to shift it over by 1. However, the outermost sublevel of an electron configuration changes based off of the element that you're looking at, right? Oxygen ends in 2p4, whereas fluorine ends in 2p5. Well, that means that we're still going to shift it over to the left just a little bit. However, we're also going to increase the peak of the graph by 1 because we're increasing the total number of electrons in that sublevel. So let's spend a couple moments, let's practice with this, and we'll wrap things up pretty quickly here today because this is a pretty short part of the first unit of AP Chemistry. So let's analyze this problem and see what we can come up with for a response here. So it says to draw an X above the peak that corresponds to the orbital with the electrons that are on average closest to the nucleus, and justify your answer in regards to Coulomb's law. So if we remember correctly when we discussed this earlier, we can label these peaks pretty easily. The very first peak down here, this is the 1s, then the 2s, then the 2p, and then the 3s. And as we mentioned before, the 1s sublevel, when we write an electron configuration, represents the electrons that are closest to the nucleus. So we're going to go ahead and mark an X at the top of that peak right there. And then it says to justify your answer in terms of Coulomb's law. Well, the 1s sublevel is closest to the nucleus, and electrons that are closer to the nucleus are going to be the ones that have the higher binding energy. Because a shorter distance between the nucleus and the electrons results in a stronger attraction due to Coulomb's law, and thus more energy is needed to remove those electrons. Electrons that are further away, such as valence electrons in the outermost shell, are the ones that are less attracted to the nucleus and therefore are easier to remove. So due to the high binding energy that's associated with the 1s sublevel due to its proximity to the nucleus, we can safely say that we have correctly labeled the 1s sublevel. In addition to this, it also says, based on the spectrum, write the complete electron configuration of the element. So we've kind of already gone and done that, but we need to make sure we write the appropriate number of electrons that are present as well. Now be careful here, because if we look, it looks like each one's going up by 1. But if I think about electron configurations, I know that in order for electrons to be in the 2s or the 2p sublevel, that the 1s has to be full. So each little bar here does not represent 1 electron, it actually represents 2. And we know that because of a full 2p sublevel is going to have 6 electrons that are in it. So when I write this out, I'm going to write out 1s2, 2s2, 2p6, 3s1. And I can safely identify this if I need to as sodium, due to it ending in 3s1. So again, just take your time, work through it. Make sure you analyze the graph very closely because some people would write this as 1s1, 2s1, 2p3, and then you look at that little half one that's there, really doesn't quite make sense. So really make sure you analyze the graph closely so that way you know what you're looking at, because the relative number of electrons, it doesn't give you a scale, doesn't give you a number. Really think about that before you go through and start writing out an answer to the question that's there. Let's look at another problem. And so for this problem, what we're going to do is we are going to draw out information on this peak. So it says on the graph, draw the peaks corresponding to the valence electrons of the element that has 1 more proton in its nucleus than the unknown element has. Well, we've already established that this is sodium with 11 protons in its nucleus. And it wants us to talk about, to draw a peak that corresponds to the valence electrons of an element that has 1 more proton in its nucleus. So now we want something that has 12 protons. Well, remember that the ending electron configuration for Na is going to be 3s1. The element that has 1 more proton in it is going to end in 3s2. So due to the fact that it has an extra proton, this outer energy level that's here is actually going to shift to the left. Because of an increased nuclear charge, we have a greater attraction of those outermost electrons to the nucleus, right? We're looking at 12 protons versus 11 protons. So we're going to shift it to the left, but because it ends in 3s2, we're also going to make the peak just a little bit bigger, because that outer shell needs to represent 2 valence electrons as opposed to just 1 now. Let's say we had a similar situation here where it asked us to write the 1s sublevel of magnesium on this. Well, we do the same thing. We're going to shift it over to the left, and we're going to shift it over to the left due to the fact that we have an increased number of protons that are found in the nucleus, resulting in a greater attraction of those electrons to the nucleus. However, We don't change the height of that sublevel because when we write out the electron configuration for sodium or magnesium, they both start with 1s2. And so as a result, we don't change the height of the peak, we just shift it to the left based off the fact that we have more protons in the nucleus. So that is pretty much photoelectron spectroscopy in a nutshell. I would make sure that you know how to read the graphs, read them carefully, know how to identify what elements we're looking at, know what each individual peak represents, and then know how the graph is going to shift or change based off of the type of element that we're looking at, as well as shift in peaks based on whether it is a core set of electrons, such as the 1s sublevel, or if it's the outermost valence electrons, and you may have to increase or decrease the height of that peak. So as I mentioned before, this is going to be a pretty short video. I hope that that covers everything we need to know about photoelectron spectroscopy. I really appreciate you watching, and if you do, feel free to leave a like, subscribe for more AP chemistry content. A little more coming down the way. Try to get a little bit more active in my participation in my YouTube channel. But hopefully we'll see you very, very soon. Bye, everybody.